So let's look at a couple of examples here. Let's classify the bond between carbon and hydrogen. Carbon and hydrogen. So you can look up tables for electronegativities. You'll find hydrogen's 2.2. Pauling originally assigned that a value of 2.2. Okay, and carbon's 2.5. Although in a later paper, Pauling changed that to 2.1. So you might see 2.1 in your textbook. What's the difference between carbon and hydrogen? A difference of 0.3. So a carbon to hydrogen bond, we say, strictly speaking, it's polar covalent. But for practical purposes, that difference is so small, we say the bond is essentially nonpolar. So CH bonds are generally considered as nonpolar bonds. What about lithium and bromine? Lithium's 1.0, bromine is 2.8. So what's 2.8 minus 1.0? 1.8. That's a very large difference. So we say it's a polar covalent bond. It's almost pretty much, it's essentially ionic. Okay, you're up there close to 2, so that's an essentially ionic bond. Now, I did give you a 2.0 threshold cutoff, right? And that's a gray area right there. So it's, the best thing to say is that it's very polar. Okay. Because there's really no such thing as 100% ionic. How can you get a 100% ionic anyway, using Pauling's formula? How might you make that for 100%? What would have to be the electronegativity difference in order for delta to be equal to 1? What's the largest possible electronegativity difference you can get? Between francium and fluorine, right? Based on his scale, what's 4 minus 0.7? 3.3. But what is 1 minus e to the 3.3 squared over negative 3.3 squared over 4? Let's put that in your calculator. Okay, so 3.3 squared, so 3.3 times 3.3 divided by 4. Okay, make that negative. Okay. Oops. Is that what I have? Okay. Oops, I'm sorry. Negative. Let's do it again. 3.3 times 3.3 divided by 4. That's 2.27225. Make that negative. And then take the inverse log of that. It's 0.06. Okay, so that's 0.066. Subtract that from 1. So minus 1, that's 0.934. So that's only 93.4% ionic. Okay, so using this formula, you can't even get 100% ionic. So it's really just, there's really no theoretical basis for this formula. He just used it to fit his experimental data. So you can just use that as a gauge, a rough gauge as to whether or not you're dealing with something that's ionic or polar covalent or covalent, non-polar or polar, right? What about sodium and chloride? Would that be an ionic bond or polar or a non-polar bond? Sodium is 0.9 and chlorine is 3.0. What's that difference? 2.1. That's essentially ionic. Okay, sodium chloride is an ionic compound. All right, so how do we reconcile this with your earlier lesson where you were told metal plus non-metals ionic, 2 non-metals covalent? Well, 2 non-metals will generally give you covalent, polar covalent at the most, all right? But if you have metal plus non-metal, okay, that's why I'm very careful when I teach this to my class. I say metal plus metal tends to be ionic. But you can see there's going to be a lot of exceptions you'll see here. In fact, a whole class of metals, the transition metals, the electronegativities are such that the difference between those and the non-metal are, if you go by this classification of bonds, they're not really going to be classified as ionic. So there's really, ionic is really just an extreme case of 100%, what you might consider 100% polar covalent, but it's really Most bonds are really somewhere in between. Okay? Okay, how about this one? Which of the following is or are true? Number one, a non-polar molecule can have polar bonds. Number two, a molecule with no polar bonds is nonpolar. Is it one only, two only, both, or neither? What does a molecule need to have to be polar? At least one polar bond. But if it has more than one polar bond, those polar bonds must not cancel each other out, right? Because due to the symmetry of the molecule. So how would you evaluate these questions as far as being true or false? Is it one is true only one is true, only two is true, or are they both true, or are neither one true? Okay, let's see. A non-polar molecule can have polar bonds. Is that true? Yes. What's the example we have? Carbon dioxide, right? It had polar bonds, but it is non-polar, so that's true. Okay, so it can't be D. A molecule with no polar bonds is non-polar. It has to have at least one polar bond, right? So this is also true. So C is correct. Good. Okay, which of the following is polar? H2O, BF3, CH4, PF5. This is the case where it's a question where you have to remember your molecular structure and geometry. Okay, so that's why I wanted you to review that. Here's water. You have a tetrahedral geometry around the oxygen atom, and the molecule is bent. BF3 is trigonal planar. CH4 is tetrahedral. And PF5 is trigonal bipyramidal. So which one is polar? A, B, or C? Or D? It's actually an easy one because you didn't even have to know the others, right? You already know one of these is polar, which is what? Water. Very good. Now, why are these other ones non-polar? Trigonal planar, you have three polar bonds symmetrically directed 120 degrees apart, right? So there's a symmetry here. So all of these polarities cancel each other out. Okay, imagine you have a tug of war where you have three equally strong people pulling on the center. It's a three-way tug of war. Okay, the same thing right here, tetrahedral structure. That's a perfectly symmetrical structure. Okay, so all of those polarities can actually, these are very, very nonpolar. These are very slightly polar bonds, essentially nonpolar, right? CH bond, you said earlier, was not even, okay, I even have the wrong polarity here. It should be what? Let's redo that, CH4. A CH bond, which way is the polarity directed in a CH bond? Carbon's more electronegative than hydrogen, so it's polarity towards carbon, right? But those are very weakly polar bonds, so, and they're all symmetrically arranged, so you expect CH4 to be a nonpolar molecule. PF5, same thing. You have polar bonds, okay, directed towards the fluorine, but all of those polarities cancel each other out. All right, let's look at this one. For which pair of molecules does dipole-dipole interaction occur? Between H2O and CO2, between H2O and HF, between CO2 and CO2, or between CH4 and CO2? What would you have to know to be able to answer this question? When does dipole-dipole interaction occur? When you have two molecules that are both polar, right? So another way of asking this question would be, in which case do you have, are both molecules given polar? So what do we know about water? Water is polar, right? So water is polar, but carbon dioxide is not, right? So you can't have dipole-dipole interaction there. So carbon dioxide is nonpolar. You can't have dipole-dipole interaction there. Carbon dioxide is nonpolar. Methane is nonpolar. You can't have dipole-dipole interaction there. So water and HF, both polar molecules.